Friends, very good morning to everyone. Today's subject of discussion is alkenes. Alkenes are also called as olefins. These alkenes are different from alkanes based on the fact that they are unsaturated in nature. They are unsaturated in nature because they do not have just a single bond like alkanes, they also have double bonds. Or these are the organic compounds which contains carbon and hydrogen atoms, and they are linked through double bonds along with single bonds. Because of this unsaturation, its property differs. Alkanes, when we look at the general formula, it was represented as CnH2n plus 2. Here, alkanes are represented with the general formula CnH2n, where n represents the number of atoms. The carbon and hydrogen are present in the ratio of 1 is to 2. The simplest alkenes is ethylene, or it is also called as ethene. It is given with the formula CH2 double bond CH2. The two carbon atoms are linked through two bonds. The alkenes word is derived from the Greek word olefiant, which means oil forming. This alkene reacts with chlorine, and the product which is formed is oily in nature. That's why they were named as olefiants in Greek, and the alkenes have been named after olefiant. Carbon in alkenes also hybridize in as that of the alkanes. This hybridization gives stability to alkenes, like it gives stability in case of alkanes. Let us look into the hybridization of alkenes today. As we know, the atomic number of carbon is 6. Its electronic configuration can be written as 1s2, 2s2, 2px1 and 2py1 and represented in this figure like 1s orbital accommodates 2 electrons, likewise 2s accommodates 2 electrons, and the 2px and 2py 1 electron. As we know, this is the ground state of carbon, and it explains that it has two half-filled orbitals. That's why it can share that electrons with the other two, and it is becomes divalent. But carbon is tetravalent, and this has been explained by the hybridization process. As we have already seen, the s electrons jumps towards the 2pz orbital, and it gets promoted, and it has four half-filled orbitals, and here 2s and 2p orbitals combines together. Then the electrons are jumped from 2s to 2pz. This is in the excited state and higher energy state. But however, this has to occur because it has to hybridize. In the excited state of ethene, the 1,2s orbital combines with the 2p orbitals, and this forms 3 sp2 hybrid orbitals. The sp2 hybrid orbital's energy is higher than that of the 2s orbital and lesser than that of the 2p orbital. That's why overall it is more stable than that of the energy they of the p electrons or that of the s electrons. That's this three sp2 hybrid orbitals look like the sp3 orbitals only, but however these are form the bonds which are shorter and fatter. These three sp2 hybrid orbitals which are formed, they lie in the same plane. And this pz orbital lie at 90 degrees or at right angles to this of sp2 hybrid orbitals. This can be represented as follows. These three sp2 hybrid orbitals, they lie in the same plane, which is represented in the blue coloration. And as they lie in the same plane, this forms a circle, and the 2pz orbitals is perpendicular to the plane of the sp2 hybrid orbitals. And out of these three sp2 hybrid orbitals, two of these overlaps with the s orbitals of hydrogen and they form the bond. Another sp2 hybrid orbital remains vacant. And when these two carbon atoms, if they have not overlapped with each other, then this carbon and this carbon looks like this. This is the central node which represents the carbon. This sp2 hybrid orbital of the carbon combines with the sp2 hybrid orbital of the other carbon by end-to-end overlap. This end-to-end overlap of this sp2 hybrid orbitals of the two carbons forms the sigma bond. When it forms the sigma bond, it looks like this. Out of the three sp2 hybrid orbitals, two sp2 hybrid orbitals are overlapped with the s orbitals of the two hydrogens in this case and also here, and the sp2 hybrid orbital of the first carbon combined with the sp2 hybrid orbital of the second carbon end to end, and it gives another bond. The red spot is the nuclei of the atom. This p orbital, which is adjacent to the each other and are perpendicular into the plane of the sp2 hybrid orbital, they are in side by side to each other. As they are not pointing towards each other, they cannot undergo end-to-end overlap, but still this p orbital has one electron in it. And the one electron of this p orbital is shared with the p orbital of the second carbon in the sideways. Because of this, when they share, it undergo overlapping sideways. This sideway overlapping gives rise to a covalent bond which is weaker than that of the sigma bond which is formed by end-to-end overlapping. And this bond which is formed by sideway overlapping is named as pi bond. It has a sigma covalent bond and also a pi covalent bond. Both are covalent bonds. The extent of overlapping in the pi bond is lesser than the extent of overlapping in case of the sigma bond. That's why the pi bond is having lesser energy than that of the sigma bond. And because of this overlapping, the bond between the two carbon atoms, it comes more closer. That's why it becomes more shorter. This sideway overlapping of the pi bonds is represented like this. The two carbon sp3 hybrid orbitals lie in the same plane and the overlapped p orbitals lie in the above and below the plane of the carbon-carbon atom. This is represented in this fashion. And this was the proposal given to explain the alkene structure by hybridization concept, and this has been experimentally proved today by X-ray diffraction studies, electron diffraction studies, and also by IR spectroscopy. This has a planar structure. As they are planar structure, if I join this, it has trigonal shape. Hence, the shape of sp2 hybrid carbon is said to be in the triplanar trigonal shape. The bond angle between the two orbitals is found to be 120 degrees, and the carbon-carbon bond length reduces because of the fact that it has a sigma bond and also pi bond, and that's why they come, two carbons come more closer and they are more overlap, and hence the bond length is 1.34 angstrom units because it has two bonds, one is sigma bond, another is pi bond. Whereas in case of alkane, the carbon-carbon bond length is found to be 1.53 angstrom units, but it has reduced to 1.34 angstrom units. The bond angle over here is 121.3 degrees, and here it reduced to 117 degrees, and overall bond angle it will be almost 120 degrees. The carbon hydrogen bond length in case of alkanes, it was found to be 1.10 angstrom units, but here overlapping is much more stronger. That's why it has become 1.08 angstrom units. It is 0.02 angstrom units lesser than that of alkanes. As they are strongly bonded because of the two bonds, sigma and pi bonds, reduce the bond length, and it also increase the bond strength. That's why the energy to break this bond is more than that of the alkanes. It has been found to be 728 kilojoules per mole, and these facts were confirmed by X-ray diffraction studies, electron diffraction studies, and high-resolution vibrational and rotational infrared and Raman spectroscopic studies. Overall, it has a trigonal shape with a bond angle of 120 degrees and a bond length of 1.34 angstrom units of carbon-carbon, and the bond strength of 728 kilojoules per mole. This is all about the hybridization of carbon in alkenes. Because of this, it has unsaturation. It has found both sigma bond and pi bond, and hence it gives a separate set of organic compounds that are alkenes. Because of the presence of these unsaturated bonds, its property is slightly differing from that of alkanes. What is this? What is this difference? And how this affects the reactivity of the alkenes and what type of reaction the alkenes occur will be the subject of discussion for the coming presentation. Till then, have a nice day. Thank you.